Welcome back. This is Fundamentals of Micro and Nanofabrication. My name is Swayam from IIT Bangalore, and today we shall continue our discussion on additive processing, and we'll start the module on physical vapor deposition. So the first lecture we will focus on some basics and get the terminology, etc. right. So let's get started. So the basic idea of PVD is something we touched in the first lecture when we looked at the introduction to all the various techniques. The idea is that you have a certain source, and unlike CVD where you make the material in situ on top of the substrate, here you have the material already made. So you already have the source in some form, typically solid form, and all you have to do is convert the solid into a vapor and then transport this as a vapor to the substrate and deposit it or condense it. For uniformity, often the substrates are rotated in order to keep this wafer clean and not contaminated. For example, if you are trying to deposit aluminum, you do not want it to react with oxygen to form aluminum oxide. So you do all of this inside a vacuum chamber, so you need some valves, some pumps, etc. The way you make this wafers differ. So you can do sputtering, evaporation. We shall look at all these techniques down the line. But primarily we use these to deposit films that are not of electronic quality. So we do not care about the crystallinity, orientation, etc. So metals, silicides, nitrides, polycrystalline thin films of various forms are often deposited through this technique. We also deposit optical films. So supposing you want an anti-reflection coating in your solar cell, or you want some dielectric mirrors in your photonic devices, for that also you can use physical vapor deposition. Dielectrics can sometimes be also deposited. They are not as great a quality as grown dielectrics. However, for various applications they do very well. Some semiconductors which tend to be defect tolerant and don't care about grain boundaries, etc. too much, or are trying to be low cost, for example CZTS, IGZO, etc. can also be deposited using physical vapor deposition. But the most important aspect, and that is the seed for the next of the lecture, is that PVD often requires high vacuum. So high vacuum means pressure much lower than 10⁻³ torr. So if you remember CVD was actually completely opposite, where the pressures were always in millitorr to torr regime. So there we have viscous flow, and we talked about Reynolds numbers, etc. For these very low pressures, those kind of concepts don't work. We now are in the molecular flow regime, and we need to understand those concepts. So let's first get the jargon of vacuum out of the way. So 1 atmosphere is typically 760 mm of mercury at sea level. Each mm of mercury is called a torr. So 1 atmosphere is 760 torr. This is an imperial unit of pressure. The SI unit of pressure is Pascal, and 1 atmosphere is 10⁵ Pascal, where each Pascal is roughly around 1 Newton per meter square, and that is 1 atmosphere is also called 1 bar. So 1 atmosphere is 1000 millibars. Okay, so these are the various units of pressure that are used. So starting from atmosphere, once you get to around 10⁻³ of 1 atmosphere, which is around 1 millibar, this is what is called low vacuum. So your atmospheric pressure CVD is typically around atmospheric pressure. This is from low vacuum to around medium vacuum is where you start doing LPCVD. So this is something we have done till now. But once you go below 10⁻³ you start entering high vacuum, from -6 to -5 very high vacuum. These are the regimes in which we often do PVD. So even though sputtering actually happens under medium vacuum, at the start of the sputtering you pump down the chamber to high vacuum and very high vacuum levels. This terminology will become a little clearer down the line. You can actually attain even better vacuum, say better than 10⁻⁹, or in extreme cases better than 10⁻²2. This is the sort of pressures you find in space. At these levels you don't typically do depositions. The pressures, it's very hard to make these sort of vacuums, and the deposition rates are too low, etc. But a lot of characterization such as MBE, characterization is often done here. The only exception to this is MBE, which is often done under under ultra high vacuum conditions. But a lot of characterization like TM, XPS, UPS happens here. So this is not what you are going to do. This is not what you are going to do. We are right now concentrating on what happens when you are in this high vacuum and very high vacuum regime. So let's first talk about pumps. What are the various pumps we have to actually get to these various pressures? So pumps come in various sizes, various techniques and various sizes. So you have to select a type of a pump for an application, and each pump promises to work in a different pressure range. So at when this is the nearly atmosphere, 10 power 3, and as you're going leftwards, you're going to higher and higher vacuum. So there are certain pumps like rotary piston mechanical pump, oil sealed mechanical pump, these sort of things work, but only work under high pressure. So once they start pumping and you get to what the base pressure of that pump, you actually cannot gain any further by just pumping it longer. So no matter how long you put an oil sealed pump to a vacuum chamber, you are never going to get 10 power minus 4 vacuum, because that is the limit of that pump. In order to get better vacuum, you tend to need different techniques. So the common ones are, for example, cryo pump, diffusion pump, but then these pumps cannot actually function at higher pressures. So what happens is that instead of having one pump, you have a series of two pumps. So at higher pressures, you use these pumps to get it down to certain low value, and once it is at that low value, then you engage these pumps to push it even further. If you want to get to ultra high vacuums, even cryo or diffusion pumps are not good enough. Then you have to do titanium sublimation pump or iron sputter pumps, etc. And these again have a certain limit. So in this case, you have a cascade of 3 pumps to actually get to minus 12. So you can see the complexity keeps increasing. The most common pumps that are used in modern age tend to be the oil sealed mechanical pumps. These are the simple vacuum pumps. If you don't know which pump you have, you probably have this pump. Cryo pumps are very commonly used. Diffusion pumps used to be very popular, but not so much anymore. They have been replaced by turbomolecular pumps or turbo pumps, and iron sputter pumps are popular for ultra high vacuum applications. Now the first concept we sort of have to understand the molecular flow regime is the mean free path. The concept comes from the kinetic theory of gases, and the basic idea with kinetic theory of gases is the gas molecules are moving around and they will continue to move in a direction until they hit another molecule, in which case they don't lose energy but change the direction, and these collisions are happening inside all the time. So what is the average distance that a gas molecule travels between two collisions? That is what is the mean free path. And that would depend, of course, on the pressure. The more the pressure, the shorter the distance. So lambda must be inversely proportional to pressure. It depends upon temperature. Higher the temperature, longer the distance. And it depends upon certain geometric factors and a few other details. So as you go to lower and lower pressure, what you end up doing is keep increasing this value of lambda. So this is the formula, just to give you some context for actual numbers. So atmospheric pressure, the mean free path is around 100 nanometers. The gas molecule is only sort of on an average moving 100 nanometers before colliding with something. As you get to low vacuum, which is say LPCVD area, this number becomes 100 micron. Okay, still pretty small. But once you get to high vacuum, which is where PVD is often done, those values are 100 meters. So the mean free paths are actually much longer than the size of the chamber itself, and that has a consequence. So this is the pictorial view of that consequence. So initially the collisions are happening at a scale that is much smaller than the size of the chamber, but once you pump the chamber low enough to high vacuum cases, the gas molecules are not so much colliding with each other anymore. They are typically just colliding with the surfaces of the chamber, right? Because the mean free path is much longer than the size of the chamber. Now once you have the concept of mean free path, then you can take it one step further and ask yourself, what is the impingement rate? And impingement rate is, supposing I had an arbitrary imaginary 1 centimeter square area, how many atoms will actually come and impact me per second, right, per unit time. So that again you can simply calculate using kinetic theory of gases. It's related to lambda and it's given by this formula. Now once you know the impingement rate, you can actually calculate one more interesting quantity, which is a monolayer time, or time to a monolayer. This is the time required to form a monolayer on top of an imaginary surface, assuming each of these atoms that is impinging on the surface sticks. So if everything that impinges sticks, how long before I form a monolayer? So that formula is just inverse of the impingement rate and is given by this. So now let's look at some of these numbers to again get the context. So at atmospheric pressure, our lambdas are 100 nanometers and impingement rates are around 10 to the power 23, right? So while sitting in this room, 10 to the power 23 atoms are hitting my face every second, per centimeter square, I think. Per centimeter square per second. And the time to a monolayer is 10 nanoseconds. And if every one of those gas molecules stuck to my face, I would form a monolayer of those gas molecules in just 10 nanoseconds, right? So that's what happens under APCVD conditions. So you get to LPCVD and the impingement rate reduces to 10 power 23 and the time to a monolayer is now 10 microseconds, but still fairly short, right? At least compared to the deposition, the time of deposition, this is very small. But once you get to -6 regimes, the impingement rate is only 10 power 14, which means it takes 10 seconds to form a monolayer. Now we are getting into regions where it takes some amount of time to form a monolayer. And if you go even further, if you go to ultra high vacuum -10, the time to monolayer is 30 hours. And this is the reason why you actually need ultra high vacuum to do characterization. So supposing you are doing TM, right? You are looking at these monolayers, you are looking at these single atoms, right? A single layer of atoms. If you do this inside a chamber where time to monolayer is less than the time it takes for you to do the imaging, you would actually just see junk all the time. The only sane way of doing the characterization would be do it inside a chamber where the time of the monolayer is much larger than the time it takes for you to take the image, because only then you have a good chance of actually looking at your sample and not just the crud that gets deposited on top of it. So this is why a lot of the characterization equipment actually like UPS, XPS require you to have ultra high vacuum, right? PVD does not. PVD is happy with these sort of times, but it's still to give you some context, right? So this is sort of a figure that captures everything we have discussed till now. There's a molecular incidence rate, there's a mean free path, there's a monolayer formation time, and all of these are a function of pressure, right? And a very strong function of pressure. Typically for PVD, we are in this high vacuum regime, and that is where we will operate. Now, just like we had viscous flow regime, in the molecular flow regime, we have certain numbers that we have to look at. So there it was Reynolds number, here it's Knudsen number, which is given by this formula. I'll not quiz you on it, don't worry, you don't have to mug up these numbers, just to make a point that unlike viscous flow regime where there was a laminar flow, and the reason it was laminar was molecules were interacting with each other. One molecule, because it was colliding with the other molecule every 10 nanometers or 10 nanoseconds, sorry, it was very much aware of its presence. So they all sort of went into these streamlines because they are always interacting with each other. So they were forced to sort of walk in a line. But in the molecular flow regime, molecules don't interact with each other at all because the size of the pipe or the chamber is much smaller than the mean free path. So the only thing that they interact with is the chamber wall. So the flow inside these, in this is very different from the laminar flow regime. It does not depend upon the pressure. It does not depend upon the characteristics of the gas so much. It actually just depends upon the dimension of the pipe that you have. So with that, we'll just come to the end of this very short introduction into the molecular flow regime and just setting up some jargon of ultra high vacuum, etc. Why do we need those kind of vacuums? In the next lecture, we shall focus more on the details of evaporation and sputtering.